Hello, so today I'm going to look at using the definitions of the trigonometric functions. So you kind of learned in the previous section that in order to define your trigonometric functions, you would just need to essentially consider a ray in standard position. Now, in any case, like for instance, you know that you can have something like this, where you have that, suppose that if you were to drop the altitude of this ray, in this case we have that it stops at some kind of ordered pair. So for instance, we know that the length of which that emanates from the origin to the terminal point is going to be r, followed by we have our x and our y. That's only if we have that the ordered pair is the following one, like x comma y. So in this case, it actually doesn't matter what the equation is, but we do have that the angle that forms, so we have that it's going in this direction, is going to be theta. So we have that r is going to be equal to the square root of x squared plus y squared, and then furthermore, we can define our 6 trigonometric functions. So sine theta is y over r, and then cosine of theta is x over r. And then tangent of theta is going to be y over x, but that's provided that the x component is not equal to 0. Now, in this section though, we talk more about somewhat some identities that relate to trigonometric functions. So for instance, we have that there's what we call the reciprocal. Okay, so the reciprocal identities basically just rewrites sine theta, for instance, as 1 over cosecant of theta. And then you have that cosine of theta. Let's actually write it over here. Okay, so we also have that cosine of theta is equal to 1 over secant of theta. And then we have that tangent of theta is equal to 1 over cotangent theta. Now, similarly, basically all that we're saying is that we can just rewrite each of those identities or functions as so. Okay, so more or less this is just rewriting. And then we have cotangent is going to be 1 over tangent of theta. Now, one way that you can kind of look at this, for instance, like how exactly did this come about, for instance? Well, think of it like this. Okay, so we know that, for instance, that if we looked at secant of theta, that we know that that's going to be r over x. But notice that if you were to basically divide by r on top and bottom, well, that would give you 1 divided by x over r. But by definition, x over r is cosine. So you have 1 over cosine theta. Now, basically, the idea is that that's being applied for each of the other trigonometric functions. Okay, so you can probably try it out in either case, like if you want to show that each of the reciprocal identities are exactly as follows. Now, one way of which that this can help us in either case is that, for instance, if we were going to look at the expression, let's say cosecant of 90 degrees, for instance. Well, cosecant of 90 degrees is actually just 1 over sine of 90 degrees. Now, you learned in a previous section that sine of 90 is actually just 1, so that's just going to be 1 over 1, which is just 1. And then similarly, we can probably say that, for instance, that um, that if you want to find, say, for example, secant of 180 degrees, well, that's really 1 over cosine of 180. But you also learned that in the previous section that cosine of 180 is that straight angle, so it's going to be -1, so that gives you -1. So it might be good to practice, like the evaluating the trigonometric functions and finding what they are. For now, let's just look at a example. So let's say that in this example, you have that um, you want to find tangent of theta. So we want to find tangent of theta where cotangent of theta is equal to the square root of 3 over 3. Now, in this case, we know that basically by definition that cotangent theta says that it's going to be 1 over tangent of theta. So what we see here is the following. We see that we have that this is going to be the square root of 3 over 3, and that's equal to 1 over tangent. Now, in this sense, this is going to tell us that you have the following. You have that tangent of theta is equal to 3 over root 3. But if we were to rationalize this by multiplying by root 3 over root 3, you would find that this is going to give you 3 root 3 divided by 3, which is actually just root 3. Now, that may have been perhaps maybe too much work, I don't know. Because one other way that we could have done this is that we probably could have just said, well, I know that similarly that tangent of theta is equal to 1 divided by the square root of 3 over 3, which would have gave you the exact same thing because you would have end up getting 3 over root 3, and then from there you just kind of simplify it as needed. So it gives you basically kind of like the same thing. Okay, now I will say that, when it comes to like your exams, even though you can kind of do every problem like in any different kind of way, um, it's probably best just stick to one solution per question. So you're not actually using multiple methods to solve a problem just so that you can say, oh, I can do this problem like 5 different ways. Well, whatever works, just one solution. Okay, so what you can probably do on your end is you can probably try to find secant of theta when cosine of theta equals to the square root of 2 over 2. Now, one way that you can kind of look at it is sort of the same way as you did over here, because you know that secant of theta is equal to 1 over cosine of theta. Okay, so that's kind of like what you look at when it comes to the reciprocal identities. Now, the other thing of which that we can look at within this section is talking about the signs. So if we look at the signs, we're talking about like, positive, negative, and so on. Now, we know that the quadrants divide into fours. and we know that the vertex right here is O or whatever you want to call it. So let's say that that's y and that's x. Okay, so and we have that that's quadrant 1, that's quadrant 2, that's quadrant 3. Okay, so that's quadrant 3, and this is quadrant 4. Now, the things of which that we happen to know is that the r is always positive. So we have that r is always positive. So r is always positive, r is always positive, and then you have that r is always positive. But notice that basically you have that the x and the y are both positive in the first quadrant. Now what that means is that basically you have that sine, cosine, tangent, and their reciprocal identities would be positive. So that means that basically all the trigonometric functions are positive. But in the second quadrant, you have that one is positive and one's negative. So x is negative and y is positive. So what that means is that only the y and the r are positive. So that means that sine and its reciprocal function are positive. So normally we tend to put like an s. So we'll put an s. Well, if you repeat that process of, looking at, that x and y are negative in the third quadrant, then that's going to tell you that if you form the quotient of y over x or x over y, that's related to tangent. So that means that tangent is positive. And then furthermore, you have that with the last one that x is positive and y is negative. So what this means is that the only one that would be positive is the x and the r, which means that that would be only cosine that's actually positive. So with that, we say all students take calculus. That way you kind of know which ones are which. So so if you want, you can always say that, for instance, if you always draw your quadrant axes, you don't need to think about the x's and the y's and the r's because then that just gets too confusing. So you have your x, and then you have the origin, and then you just say, yeah, that you have A, S, T, C. So then that's kind of useful because then you know that if an angle terminates in quadrants 1, 2, 3, and 4 respectively, then you know that it's going to, what sign it's going to take on. So yeah, that's quadrant 1, that's quadrant 2, that's quadrant 3, and then that's quadrant 4. Now, you're not really expected you're not really expected to kind of know like what signs each one takes on. And so what I mean by that is like that cosine is positive in quadrants 1 and 4, and then sine is positive in quadrants 1 and 2, and so on. But, eventually you'll kind of get it down to where you're able to say that, for instance, that they're both, yeah, that they can be positive in multiple quadrants. So, for instance, if I have that, um, let's say that you have that cosecant of theta is negative, but then let's say that um, you want to know the sine of tangent of theta. Okay, so in this case, if you have that cosecant is negative, that means that basically the possibilities are quadrants 3 and quadrants 4 because you have that sine is negative in both these two quadrants. Furthermore, like if I was to look at a different one, so like for example, if I have cosine of theta, if I say that cosine of theta is positive, and then I have that I'm going to look at secant of theta, well, the possibilities basically are quadrants 1 and quadrants 4. Okay, so one thing that you can do is a bit of analysis, for instance, but it's not very major if you think about it. But one thing that we can do is look at degree measures. For instance, if you wanted to determine like where or what the sines would be, for example, like if you had that the angle measures were 65 degrees, you know that this would be indication that uh, that that would be all the trigonometric functions that would be positive because it's in the first quadrant. So in that case, like we'll just put all, and then we can put like quadrant 1, for instance. But if you have that it terminates in, let's say, 195, well, where is 195? 195 is 15 over, so in that case, we know that this is 180, but if you go another 15 degrees, that's 195. So in that case, that's going to tell us that that's in quadrant 3, and that's only going to be for tangent. Okay, well, go ahead and try the following though. Like suppose that you had that there was an angle measure of negative 30 degrees. Which quadrant is that in? And also, what signs would we be dealing with that are only positive? Now, one of your hints is that basically you can actually just draw negative 30 degrees in the x and y plane. So negative 30 degrees would look something like this. And then we have that it goes in this direction because it's negative. So we'll just put that that's going to be negative 30 degrees. And I'll just kind of leave it at that in terms of, like how do you determine the signs of the trigonometric functions, and then also like what quadrant is it in. So before we get into some ideas of fundamental identities, let's go ahead and just look at, for instance, a circle. So this is more or less like the domain. So if we look at, for instance, a circle that has radius 1, so we'll just say that that has 1 and that has 1. Now, similarly, if we kind of like draw our ray, which goes like that, and then we know that basically this drops down like so. And then furthermore, we have that this is going to be r, this is going to be x, and this is going to be y. Well, consider it like this. If we choose any angle along here, so if we choose any angle, and that angle is theta, then we know that for any point that lies along here, that the ratio, let's say for example the ratio of y over r, it's always going to be less than or equal to 1. Okay, now in that sense, by that definition, we have that tells us that sine of theta is going to be less than or equal to 1 by that definition. So what that's telling you is that sine will be no bigger than 1, or it's going to be less than or equal to 1. Well, similarly, if we were to reverse this, like if we were to go, let's say like in this direction, then in that case, like we have that even if we were to choose somewhere along here where we have our angle theta, so like let me just do this. So let's say that that's -1. Well, in that case, it's more or less the exact same thing. If we follow along here and we form our angle with the initial side and the terminal side, then in that case, it's the same thing. You're going to have that -1 is going to be less than or equal to y over r. Okay, well, if that's the case, then that tells us that this is going to be sine theta. So essentially, this is telling us that our sine function is bounded below by -1 and above by 1. But similarly, that means that -1 is less than or equal to cosine of theta, and that's less than 1. Okay, so that kind of establishes for cosine and sine. Now, another thing that we can do is look at, for example, the circle. Like, so let's say that we use a circle. Now, notice that this is our x and this is our y. Now, if we follow along here, you have to keep forming the ratio of the y over x. But notice that the x is getting smaller, but y is getting bigger. So, or it's approaching 1. So as we do that, then you have to realize that tangent is going to just become very large. And similarly, if we were to follow along here from going in the reverse direction, you have that the x component is getting smaller and smaller, but it's negative now. So that means that it goes to very large negative values. Well, that's really just a fancy way or a roundabout way of saying that tangent of theta, it's a real number. Now, some people, they just write it like this, where you have negative infinity is less than tangent of theta, and that's less than infinity. That tells you that basically tangent can be anything. Now, if we were to look at the reciprocal functions, basically for secant of theta, you have that, well, if you use the definition and you just kind of work it carefully, you'll see that secant of theta is going to be greater than 1, or that secant of theta is less than or equal to -1. And then similarly for cosecant, you have cosecant of theta is greater than or equal to 1, or cosecant theta is less than or equal to -1. So this more or less kind of tells you the domains of those functions. So what if we were to consider some possibilities? For instance, we know that it's pretty reasonable to say that there is an angle measure that gives us that cosine theta is equal to 1. Those possibilities are that theta is equal to 0 degrees or 360 or any other coterminal angle. Similarly, if we were to say, for example, that sine of theta is equal to 0, well, that's also possible because you have that similarly that can be 0 degrees, 360, and actually, I forgot 180 degrees. But there is no way that, for instance, that you could choose a value that is outside of its limits. So like, for example, I know that there's no such thing that cosine of theta will equal to 4. This is just not possible. So in that case, like for instance, we can look at, for example, if we have, if we have, say for example, like cotangent of theta equals to -0.9999, and then we have cotangent, or not cotangent, but cosine of theta is equal to negative 2.5, and then let's say that we have cosecant of theta is equal to 0. Well, if we go through the process of just like looking at these values, now notice that if tangent of theta is a real number, that by implication means that cotangent of theta is a real number. So what that means is that this right here, that is possible. But cosine of theta equals to negative 2.5. Negative 2.5 is actually less than negative 1, which means that this is not possible. Cosecant of theta, well, look at it like this. This can't be possible because we said that it has to be greater than 1 or less than negative 1. So in that sense, there's no way that those values will ever equal to 0. So we just know that that's not going to be possible at all either. Now, what I want to do essentially is sort of just look at, say for example, that we were to consider some identities as we conclude this section. So we look at some identities, and basically we start with the most basic idea, like x squared plus y squared equals to r squared. Now, if I was to basically divide everything by r squared, then this would give me that I have x over r, and that's squared, and that's y over r, and that's squared, and this is equal to 1. Now the reason that I needed to use the circular disk with radius r is because it's very similar to what we have here, like when we have like the circle, and then we have that, you would draw your ray, and then you would have the x and the y. So in this case, the radius would have to be r, and that's going to be r. That's negative r. That's actually negative r also. So we're just kind of like keeping it in general, where of course like right here, that would be theta. And that's similar to what I was showing you in this circle right here, but this is when the radius is actually equal to 1 in this case. So that's why we call it the unit circle. And you can kind of play with this where you see like the rotations happening. Okay, now furthermore, what we could probably do is reduce this even further. Now notice that basically this reduces to cosine squared theta plus sine squared theta equals to 1. Well, this is one of your first identities. Okay, now in any case, what we do have here is that if we were to say, for example, yeah, like let's say, for example, that we, let's see, okay. Another thing that we could probably do here is look at if we were to let me see, because we have that with the original graph, we have x squared. So x squared plus y squared equals to r squared. So instead of dividing by r squared, what if we divided by x squared? If we divided by x squared, basically that would give us tangent squared theta plus 1 equals to, let's see, yeah, so that would be secant squared. Okay, now we can do one more in terms of like looking at another identity. another identity that we have here is if we divide by y squared. Now, if we divide by y squared on both sides, that gives you cotangent squared theta plus 1 equals to cosecant squared theta, which, again, if you want to derive it, you can just by dividing um, by y squared on both sides of the equation. Now, these are what we call the Pythagorean identities. And another terminology that we can use is that this is the fundamental identities. And in that case, cosine squared plus sine squared equals to 1. That's like one of the most important formulas that we'll be using in this class. Now, another thing that we can probably look at, for example, is what we call the quotient identities. So the quotient identities is whenever we form the quotient of the two trigonometric functions. So like, for example, if we look at sine theta over cosine theta, well, notice that, for instance, that this is going to be, by definition, y over r, and this is x over r. Now, this gives us y over r, but multiplied by r over x, which equals to y over x, which is then equal to tangent of theta. So what that means is that basically we've identified another formula or identity that tells us that tangent of theta is equal to sine theta over cosine theta. However, because you've already looked at reciprocal identities, that would imply that cotangent of theta is equal to cosine of theta divided by sine of theta. So we have our another identity. Okay, now let's say, for example, that we want to find some of the remaining trigonometric functions. Now, one thing that you'll realize is that there's multiple ways to kind of like solve a lot of these questions, for example. So let's say that we have that tangent of theta is equal to negative 15 over 18. And here we're going to say that theta is in quadrant 2. So we'll just say that we want to find the 6, well, we'll say like this, remaining trig functions. Okay, now we have many different methods that we can use. We can use the fundamental identities or whichever that you want. So, for example, we know that we can actually use that tangent theta squared plus 1 equals to secant squared theta. So what we'll do here is we'll just plug this in as negative 15 over 18, and that's going to be squared plus 1 equals to secant squared theta. Now we're already told that that basically the theta value is in quadrant 2. So what that means is that if it's in quadrant 2, no matter what it is, we know that the only one that's going to be positive is sine. Okay, well, if that's the case, then let's use our calculator. So we have negative 15 divided by 18. And let's go ahead and square that and add it to 1. And then let's go ahead and take the square root of that. It is possible that, yeah, I think there's a, actually, yeah, there's, let's do it like this. We'll do it like this first because it's giving us some nasty numbers. And let's just change this to fraction. Okay, so that's going to be root 61. Okay, so let's go back. So this is going to be 61 over 36 equals to secant squared theta. So that tells you that secant of theta is equal to negative root 61 over 6. Okay, okay, so by this process we can actually figure out from here that that cosine is equal to negative 6 divided by root 61. But if we reduce this even further, what you'll basically kind of notice is that that this is going to give us negative um, negative root 61. No. Yeah. So we're going to have to, let's go ahead and just do it like this, where we will multiply by root 61 over root 61, and this is going to equal to negative 6 root 61 divided by 61. Alright, well, at this point, we have many things that we can do because we know what tangent actually is and we know what cosine actually is. So, what we can do next is probably just go ahead and solve for, let's see. Okay, so far we have secant, we have tangent, which means that we have cotangent also, but I didn't do that one yet. Okay, so let's say that we want to find our sine function. Well, we know that tangent of theta is equal to sine theta over cosine theta, which by this process, this tells us that all that we need to do is take sine theta and set it equal to tangent of theta times cosine theta. So that's going to be negative 15 over 8 multiplied by negative 6 root 61 divided by 61. Now, in this case, what we're going to see, so that's an 18 actually. Okay, now what we're going to see basically is that this is going to reduce a little nicely because essentially you have that the 6 into the 18 cancels out, so that becomes a 3, but then the 3 into the negative 15 becomes a 5. So that means that sine theta is equal to negative 5 root 61 divided by 61. So we found sine theta, which by this process we can actually find cosecant. So cosecant of theta is just going to be, that should be positive. That's going to be 61 over 5 root 61. But if you simplify this, basically you'll find root 61 over 5. So that gives us cosecant of theta. Now, okay, so all that we were missing here was cotangent. So we have cotangent. Cotangent is going to be negative 18 over 15. Now, one thing that we didn't really take care of, to be honest, was rewriting this, so like negative 6 over 5. Personally, I feel like, maybe it would be better to probably reduce it first. That way we don't have to deal with these nasty numbers. But it's going to end up the same though anyways. So, whether you reduce it or not, it's going to end up the same way anyways. Now, Interestingly enough, like whenever we are in class, normally a student will basically just say, but if I already know y and x, why don't I just form a right triangle? Then from there, I know that y is 15 and the x is 18. So that means that basically you would have that this would give you, well, it's going to give you basically like kind of like 5 and then root 61, which in this case, that's going to reduce a little nicely, I think. 5, 6, in a second, 3. Well, actually, it would be 3 root 61, so let me just get rid of that. Yeah, so it'd be 3. Okay, now, in either case, like this is actually more preferable in this case, even if you would have reduced it though. So you should reduce it probably, and just think like similar triangles. Now, one thing though that we can look at next is the following. So like for example, what if you had that you know, you happen to know that, for example, that of cotangent of theta is equal to -7 over 24. Now, in this sense, well, if I wanted to find any other trigonometric functions, basically we're going to have to go through a process of like a little bit of like knowing like where the functions are with respect to the quadrants. So like notice that you have that cotangent is negative, but you're trying to find both sine and cosine. Now, cotangent is negative in quadrants 2 and quadrants 3. So, quadrants 2 and 4 actually. So notice that in finding sine, well, in finding sine, we actually don't have enough information technically. So let's just add that that theta is in quadrant 4. Okay. Now, let's say that, for example, that we know what cotangent is. So in this case, that would mean that we could probably just use, instead of using the fundamental identities, what if we were to just use the definition? So we know that basically that it's in the fourth quadrant because that's what we're going to say that it is. And we know that that would mean that you have a rotation of like so. But notice that cotangent would have to be the x over the y. So in that case, that means that this is going to be 7 and this is going to be 24. So in any case, we just need to figure out like what is the radius. So if we take 7 squared plus 24 squared, it should be 24. Yep. Let's see what we get, and let's take the square root of that. Now, in any case, that gives us 25. So we have that this is going to be 25. Okay, well, based on this, accordingly, we know that that's telling us that sine of theta is negative. Okay, so what did we learn here? Well, basically, we learned that the x was equal to 7, the y was equal to -24, and then the r is equal to 25. So what that means is that you have that that's going to be -24 over 25. So that gave me that sine was -24 25ths. So what about cosine? Well, with cosine, the things that we do know is that cosine is equal to positive 7. So that's going to be 7 over 25. Of course, our scale is not correct. I mean, I'm not going to say that it's not correct, but it's not to scale. So that's going to be 7/25 in terms of like what is those two functions. Okay, so I did that without using the fundamental identities, which that's just to show you that you can do many things. But just so that you know like what formula did I use technically, I use x squared plus y squared equals to r squared because I already knew what x was. X was -7 or positive 7, and then y was equal to -24. So we just had to be careful with that in terms of like the labeling of it. So what I'll basically kind of like conclude with is that you're more than welcome to use any specific identities as it relates to solving for trigonometric functions. The key is that you just need to know like, what works best for you. So for example, I know that cosine squared theta plus sine squared theta equals to 1, but if I rewrite it, I know sine squared theta equals to 1 minus cosine squared theta. But then if I do that, that means that I can actually say sine theta is equal to plus or minus the square root of 1 minus cosine squared theta. So you can kind of see that, okay, those fundamental identities can lead to more formulas in a sense. And then the same thing goes for r squared equals to x squared plus y squared. So what I'll do next is I'll just say, go ahead and try to find the 6 remaining trig functions if sine of theta equals root 2 over 6 and cosine of theta is less than 0. So at that point, basically you know that essentially if you were to graph this in the x and y plane, you know that basically that sine is positive, cosine is negative, so in that case we know that it can only be in the second quadrant because it's positive and negative essentially. So that tells you that the angle that formed looked something like that. So in this case, like you have many different options that you can do to figure out, what is the remaining trigonometric functions. So I would probably say, if you want to use cosine squared theta plus sine squared theta equals to 1, you can because that's going to give you cosine squared theta plus root 2 over 6 squared equals to 1. Now, I'll just kind of leave it at that because you can kind of see that you can solve for cosine, but don't forget that it's going to be negative. Once you get cosine, that means that you can get basically cosecant, secant, tangent, and then cotangent. Okay, so as you kind of work through these, be sure that you kind of do identify any little shortcuts that you can come up with in terms of like finding those solutions. Because when it comes to the exam, it's not going to be necessarily uh, keen to just one way, essentially. But just remember that you're not required to perform multiple methods. Okay, so that'll be it, and let me know if you have any questions. For now, mostly you should be able to not really necessarily use the calculator very much, aside to the small computations that we used. Okay, so um, just make sure that you do that. And also remember that in any case, a lot of your questions that you end up with, it's going to come back to like Pythagorean theorem. So Pythagorean theorem is actually going to be pretty useful for our questions in this course. And you can see that we kind of used it with respect to the trig functions. Okay, so that's going to be it. Have a good day. And in the next section, we're going to be talking more about the acute triangles and also its applications. Because eventually you'll want to be able to do those applications. Like, for example, if you know the height of a pole and you know the angle measure, you can find how far away is that base of the pole to that site of elevation in this case.